2, 1. All right, so welcome in. The goal of this video is going to be to try to convince you that the pressure within a fluid, okay, based on the weight of that fluid, can be found at any depth without actually knowing kind of what volumes or areas are being occupied. So there's a few assumptions. So hopefully you're okay with knowing what a fluid is. Okay, I can put up a link up above there, kind of the distinguishing features between solids, liquids, gases, plasmas, okay, and which ones are a fluid. So for the sake of this video, it's going to be good enough if you know that a fluid is simply either a liquid or a gas. Now, the other assumption, of course, is, well, what is weight? So this will kind of bring you back to forces. So weight is an actual force, okay, and that is caused by gravity, so the pull of the gravity, so it's downwards, but we're just interested in the magnitude. And if you wanted to know what the magnitude would be of the weight, it is nothing else but simply multiplying the mass of the object times the actual acceleration due to gravity, which we typically just say g, and I'll use 9.8 meters per second squared for that. Okay, so now jumping in and thinking about pressure. Before I jump into the pressure calculation for the fluid, let me kind of take a step back and, make a recall for you if you wanted to find out with regards to pressure. And let's say we had a solid instead of a fluid. So we're just dealing with a solid itself. So if you wanted to find out what the pressure is, you know that it is nothing else but simply the force exerted, and that force has to be perpendicular to the surface area. And now if you take an actual solid, and let's assume that it's maybe a rectangular prism of some kind, okay? All right, so voila, okay, so there it is. So let's imagine that this is just a solid, and we wanted to be able to find out exactly what the pressure is that is being exerted by this solid by basically the entire weight of that solid. Now, if we knew what the mass of this is, then of course we can just take the mass, we can multiply it by g, by gravity, and we would obtain the weight. And then once we have the weight, then we can find out what the area is, okay? And that particular area, since this object is sitting on that area, then we can take that area and then we can take the weight divided by the area, and we would find out, okay, what the answer would be. So, if you want to see kind of that concept, okay, I can put up a link up above there for you. Now, I just want to show you that if we don't know the mass, but we know the density of this particular object, right, of this solid, we can do the same. So I want to just kind of break this down in an example. So let's imagine, I'll give you some numbers so that it gives you some idea and some context to think about. Let's say we're talking about aluminum. And we know that aluminum's density, so this, density would be rho, is equal to 2.70, at least the average, okay? And this is the density that we would have. And this would be kilograms per meters cubed. So, please recall that for density, it's just simply mass over volume. So let's say that's what we had. And we knew what the dimensions were of this, particular prism. So let's say that, maybe, this was 2 meters, maybe this was, let's say, half a meter over here. And then maybe the height itself, so it looks like it's a little bit bigger. So let's say this is 3 meters. So we have all of this information. All right. So what we would do is, if we wanted to find out what the pressure is, once we are given a density and we have the dimensions, then this is definitely a doable problem, because of the fact that we could say, okay, well, pressure, I need to know the force, which is going to be coming from the weight, and it's going to be mass times gravity, okay? And then this is going to be divided by the actual area, okay, that I have, right? So that's what I need to find out. So I need to find out this mass okay, I only have my density. So how will I do that? Well, in order to do that, so if you take this item right here and figure this out, so I'm going to just kind of shift this over on this side, you of course can see that you can rearrange this for mass, right? You can multiply both sides by V, as I am doing right now, and then the V will cancel, and all you're going to have is mass is equal to the density times the volume. So what's interesting is that since I already know what the density is, 2.70 times 10 to the 3. Notice it's kilograms per meters cubed, so everything is kind of in meters there. So I'm gonna be okay on the units. And then I need to multiply this by the volume. Well, the volume here, so if I would do that, is going to be nothing else but 2 times 0.5 times 3, right? So 2 times a half is 1, and then 1 times 3, this is going to be 3, meters squared. So what I would have is, I could say this is meters, cubed, not squared, because of the fact that it's volume. So once I have this, I can find out what the mass is. So the mass of this entire thing, okay, so you can certainly change this. So 2, 7, 0, 0, okay, if I get rid of the scientific notation there, right there for myself. So times 3, so I can put that in here. And I'm going to get quite a bit of mass there. So 1.8, so 8.100, this would have been kilograms. And once I have this, of course, then I can just substitute it back in and start to calculate my pressure. So my mass, all right, so check, I have that. G, which is 9.8, all right, check. Now I still need my area, but the area is very easy for me to find because it's just 2 times a half, which is going to be 1, meters squared in here. So this is just divided by 1. And there is my pressure. So now I can just take this, multiply it by 9.8, divided by 1, and it still is going to be the same. Now I'm going to just I'm not going to be rounding anything because my goal here is to try to explain to you how you can find these pressures. So far, so good, right? You might say that, okay, well, then this isn't that bad. This would have been in pascals because it would have been just simply newtons per meters squared in terms of the answer. So approximately, 80,000, okay? So give or take a little bit. So that would have been the pressure which is caused by the weight of this particular solid. So in this case, it's aluminum, right? Now, for solids, it's pretty easy because they're rigid, right? They don't change, they don't kind of flow out, they don't move around. They're unlike fluids. But what if we wanted to be able to figure out what the pressure is, okay, in a fluid due to the actual weight of the fluid above it? Right? So at any point in time, as you go deeper and deeper and deeper, you can imagine that there's more and more pressure because of the fact that there's more weight on top of you. So if you go in 1 meter into water, for instance, well, there's quite a bit of water on top of you, right? If you go 2 meters, well, now there's more water on top of you. So you can imagine that, if you're looking at a solid and you can say, well, if the height was bigger and bigger and bigger and bigger, you can imagine that, well, the pressure is going to be more and more because of the fact that we have more mass sitting on top of a surface area. And this is a very interesting point in physics that, everyone who's studying pressures in fluids should understand. And you're going to see something kind of a little bit of magical coming out because it will turn out that we're not going to actually need the volume. And we're not going to actually need the actual surface area that the object, in this case the fluid, is sitting on. All right, so let's jump in and really give you the kind of gist of how this video is set up. But hopefully what you have just seen in the calculation will help you. So if you have, and this is, let's imagine, okay, so we have some particular liquid, and it maybe is water, right? So this water, okay, is sitting over there, and it's super deep. So we don't even know how deep it might be. And someone comes along and says, okay, well, you know, I would want to know, okay, if I was somewhere over here, right? So here, this is where I was. I wanted to find out what is the pressure that I'm going to be experiencing due to the weight of this particular fluid. And it could be water, you know, it could be, you know, fluid is, gas is also a fluid. So maybe, you know, you're just kind of have air on top of you and you're thinking about this pressure. Now, what I'm going to assume, at least for the time being, up above here, so obviously if this was an actual, like maybe a lake or an ocean, you know, you obviously have air here. Now, air, because it's made up of particles, so it's basically various gases that we have. So air, okay, you know, above it, there's more and more particles, so there's also pressure in front of that. But what I'm going to say is, I'm going to say, let's remove the air for the moment. So let's remove this so that it doesn't cause us any more chaos in terms of calculation. So let's remove this air, and let's say it's gone. I know that it's not, okay, reality for the sake of this example, but let's just remove it so that we're not worried kind of what's sitting there. And I'll come back to that air concept in just a moment. And all we're interested in is what is the pressure caused by the fluid up above. So we're going to be taking in the approach that I have just done. And what we're going to do is we're going to say the following. Okay, well, if it was a solid, right, maybe I could construct, right? So I can just say, okay, what if I could construct, okay, just as I did with the solid. And what I would do is, you know, I could construct all the way up, right? So all the way up to the surface, right? So I could do this volume, right, which is going to be right at the surface. And this volume, okay, so as you can see there, okay, so let me just kind of make it a little bit straighter. So what if I was capable of doing this? Of course, it's a liquid, okay, in this case, that I have, or a fluid up above me, right? And I am interested in, if I could have this structure just as I had here, then I could do exactly the same process. So I can ask the question, okay, well, I have a certain surface area over here, right? This kind of rectangular prism takes up a volume, but this volume is nothing else but that area times the height. And now here I am referring to the height as the depth, right? So that's what depth are you at? So this is my height, or, you know, you can write the D for depth if you wanted to. So that's what I'm referring to. Okay, so far so good. Basically looks kind of the same. And now, moreover, someone tells you that, hey, you know exactly what fluid you're dealing with. Maybe it is water indeed, right? Maybe it's some other fluid, okay, that you're dealing with. It doesn't really matter. But if once you know it, you can say, okay, well, now I know the density of this fluid. Just as I said here, you know, what if I knew that it was aluminum? Well, then if I know the aluminum, then I know the density. If I know the density and I know the kind of shape of the actual object that I have, I can calculate the volume, I can calculate the area, you know, and from there I can figure out what pressure this object is exerting. So here, you know, I'm kind of trying to do exactly the same thing, where I'm going to say, okay, well, if I took this object, I could certainly pour in the liquid into here and do all of those calculations because now it's a nice rigid shape. All right? Now I'm going to show you that we don't actually need this because everything will fall apart. And all you will need is the density, so meaning you need to know what fluid you're talking about, and you will need to know and tell me, okay, under what depth are you interested in to find out the pressure that is present? Okay, so let's try it. So how would we do that? So let's go back and think, okay, well, the pressure at a particular depth, okay, or the height to the surface above, is equal to the force divided by the surface area. Now, my surface area, okay, would have been, I'm just assuming that this is my surface area over here. My force is the actual weight, which was nothing else but mass times the gravity of this fluid, okay, that is present. So far, it's basically the same thing. And now, as I've done above, we know that because of the fact that someone gave us the density, we know that the mass was equal to the actual density times the volume that it occupies, right? So that's the same thing as I did over here. So there's nothing different, okay, from this. So this was coming from right here. So that's the mass. Okay, so far so good. Now I'm going to take this a little bit further, because what I'm going to say is that, hold on a second. I know what this kind of prism looks like, right? This is nothing else but the density. So the volume is the area multiplied by the depth, right? So that's the volume that I have, because it's nothing else. So notice it's area and the height or the depth that I'm working with. Now, the reason why I do that is because now I can substitute this back into the formula for mass. So my mass is equal to the density times the area and height. So that's my mass. Then my gravity still stays the same. So this is going to just multiply that. And then I have my surface area, which is there. But notice what happens now. The area is gone. It falls apart because it's area divided by area. And look what you have come up with. What you've come up with is that the pressure at a particular depth here, so at this depth that I have, so this, from the surface all the way to whatever depth that you want, is actually equal to nothing else but simply the density of the fluid you're going to talk about, the depth that you are interested in, and then G, but G is a constant, right? This is just gravity, which is 9.8 meters per second squared. So this is amazing, because what it tells us that for any fluid that you want, it can be air, it can be water, it can be even blood or any liquid, okay, that you have, you can find out the pressure due to the weight that is sitting up above it by simply knowing the density and then knowing what depth you're interested in. So as an example here, if someone said that, okay, well, you have a lake. Now, of course, again, we're assuming that on top of the lake, we kind of remove the air, because the air is also a fluid. But I'll talk about that in a moment. But let's imagine that you don't have it, and you're only interested in the pressure caused by that fluid. So if you have a lake and you said, what is the pressure, okay, at a depth? And let's make the depth kind of arbitrary. Let's say it's maybe 25 meters. You want to say, what's the pressure down there? So now what you would have to know is you would have to say, okay, well, what's the density? Now, the density for water, okay, more or less kind of the average density that we know is actually, 1,000 kilograms per meter cubed. Now, this is more or less around kind of 4 degrees Celsius, but we can assume that it's, ever so slightly somewhere around there. So if I know that, then this problem is very easy, because I don't actually need to know anything. I can just say, oh, your pressure is equal to the density, which is going to be 1,000 kilograms per meter cubed. It's going to be multiplied by the depth that you have, right, that you're going through. So this particular depth, okay, is going to be 25 meters. And it's going to be multiplied by 9.8 meters per second squared. Now, all of the units have to be in SI units, so kind of standard. So for mass, right? Okay, sorry, for density, you need kilograms per meter cubed. The height itself, make sure that it's in meters. Okay, and then the 9.8 is meters per second squared. So notice that all of these units, okay, so what will happen is that they'll cancel off. And this indeed is going to give you, okay, the answer in pascals. So if I wanted to calculate this, I would just say 1,000 multiplied by 25 multiplied by 9.8. Now, it seems like it's a lot of pressure, right? So it's 245,000 pascals as the pressure at that depth. And the higher, the deeper that you go, more and more pressure you will experience, because of the fact there's more and more fluid on top of you, right? So this is a very neat example that you can have. Now, you can take this and stretch this even further. You know, here's another example, okay, that you would have. Now, this is sometimes an example which you might run into, for example, for some healthcare applications. So imagine that you had an IV. Now, this IV is kind of closed in, and inside of here, okay, you had some kind of a liquid. Maybe this is a blood transfusion, all right? So that means, let's imagine that maybe it's some kind of blood. Now, blood is a little bit more dense, okay? It's let's say 0.03 times 10 to the 3, kilograms per meter cubed. And if someone tells you that, right, and then this IV is running, now this is something that you may not kind of think about, but let's say that this is the entry point, right, where the patient is hooked up. And you wanted to be able to know, what is the pressure at that entry point, okay, to the patient? Because all of this inside of here, this is all, right? So as you're going through an IV, so all of this is going to be the actual fluid. So you can say, oh, okay, well, you have, so to the entry point, you would need to know what the depth, okay, or what the height, how high has this fluid been rising. And it's independent on how much fluid you have in there. And that's kind of what I was trying to show you here. Notice that the volume kind of fell apart. The area kind of fell apart. All you need is the density, and you don't need to know what the depth is. So here, if someone says that, maybe this IV is set up, and this is 1.5 meters, okay, above, right? So from the top of the actual fluid to the entry point, and someone tells you what the density is, then you will know what the pressure is. Pressure is nothing else but simply the density multiplied by the height, okay, of that IV, how high is it, so how much liquid will it have above, and then multiplied by gravity. And then if you put this all in here, so it's going to be 103 times 10 to the 3 times 1.5 times 9.8, and there you have it. And you're going to be able to find out what that answer is. So for this one, so we have 1.03, so this is times 10 to the 3. All right, so this is going to be all multiplied by, this is 1.5, that's the height, times 9.8, let's not forget that. And there you have it. So you would have, and again, I'm not rounding here, okay, although if I was rounding, I guess this has 3 sig figs, this has 2. So we can approximate this to 15,000 pascals as the pressure. And that's pretty neat. And that goes on for all fluids that you have. Now, fluids are not just liquids. As I said, you might also be capable of calculating the actual pressures from gases. And air is one of the most common ones, okay, that we kind of deal with. So we're sitting and walking around the earth, but what we don't realize is there's a lot, right? The atmosphere itself. So around the earth, so if you were thinking about this, so here, if this is our earth right here, and we're walking around this, so there is, there's a certain kind of, it's almost kind of like an atmospheric where there's a lot of gases, right? We don't really see them. I mean, now maybe more pollution, we might see some, but there's gases, okay, right above. But gas is a fluid. So you can actually calculate, if you know, okay, this height right there, and if you know the average density of air, what that might be, then you can figure out what the pressure is, right, at the actual surface area of the earth. Now, I'm going to kind of throw this at you and maybe do the reverse as an example. And what I mean, okay, within here, so let's calculate something pretty neat. I'm going to actually tell you that the pressure, so we actually know that the pressure, now this is at sea level. Of course, the earth isn't really fully out, kind of flat all the way around, right? There's mountains, so there's some higher altitudes, some lower altitudes, okay? But at sea level, the actual pressure is pretty large. It's 101,325 pascals. So that has been calculated. And by the way, this value is known as, so it has a different unit, and it relates back to the atmospheric pressure, so to the air around, and we have called this 1 atmosphere, 1 ATM, and it is equivalent to 101,325 pascals. That is kind of at sea level. That is the pressure that we don't feel it because now we're kind of acclimated to it. Our bodies and so on have over time have acclimated ourselves to this, so we have no sense of feeling. Okay, we only sense the changes in pressure, right? So that's kind of what our bodies are susceptible to. But that is the actual pressure that is exerted from all of the particles that are up above us that, we pretty much don't see. And that is 1 atmospheric pressure. So I'm going to keep it in pascals. So let's imagine that. Now, if I told you, and this is give or take, so because gravity is trying to hold these particles in. Now, a gas like air is much more compressible than a liquid. Liquid is not really compressible at all. But a gas is very compressible. So technically, all of the particles, oxygens, carbon dioxides, and so on, they might be more concentrated towards the surface because the gravity is trying to pull it down. So it's kind of compressed in. And the further and further you go up, kind of the less and less you have. So technically, the density changes. It's much more dense by the sea level than it is, kilometers upwards. But so we can figure out maybe the average density between them. And let's do that, okay? Let's try to find out what the average density might be, okay, for this. So if I told you, for instance, that the distance that you would have, so from the Earth to kind of almost the end of the atmosphere. So the atmosphere, if you go straight up, this actually is approximately 120 kilometers. And you can look this up. I mean, sometimes people say 100, sometimes a little bit more, but let's say it's 120 kilometers. So in meters, this would have been 120,000, of course, because if you can convert the prefix back. So if we know that, then we can find out what the density is. So pressure is equal to the density times the depth times the gravity. Now, I just told you that the pressure, and this is kind of at the sea level here, so right, of Earth. So if that is 101,325, the density I don't know, I'm trying to find it. Now this is 120,000, right? So that's the depth or the height, okay, of how much air is up above us. Okay, and then the last one is 9.8 meters per second squared. Notice that now you can manipulate this and you can solve. So if you divide on both sides, you can find out what this is, right? So I have to be careful. This is density. Be careful how I write it. So I write it as a rho. And this would have been 101,325 divided by, and in the denominator, 120,123, okay, and then also the 9.8. So if I take out my calculator, 101,325 divided by 120,123, okay, and this is times 9.8. Notice I put it in brackets. So if I do that, it's very, very small. So the density is equal to 0.086. I'll just put it into kind of two significant figures. And this would have been in kilograms per meter cubed. All right. So that's kind of the average density that you would have. It's actually more dense, okay, towards sea level. So if you kind of look this up, okay, I also did a video on density. You can put it up above there, right? So you'll notice that at sea level, it's actually, 1 point something kilograms per meter cubed. I can't remember exactly. But this is the density on average between 120 kilometers up above us. So you can see that it really fades away, right, as you're going through. All right, so that is all, okay, that I have for you. And I've given you a few examples in here, kind of explained to you how you would calculate what the actual pressure due to the weight of a fluid would be. Now, please don't forget now that in the examples, what I've done is I've kind of removed, so for example, here I removed the air. Now, if you would add the air on top, then you would have to add the pressure from the air plus the pressure from the water or liquid combined together, unless, you know, you've closed something off and the air actually can't press down on it. All right, and then you just vacuumed off all the rest. All right, so this is it. I hope that you found the examples and the explanation useful, and we'll see you in a future video. Bye, everybody.